from this section, one more example left, I want to work on that before moving on. So the last two examples that we work on, it was like, okay, this is the objects we have, these are the members, go ahead and find the shear stress or the normal stress in different part and somehow trying to find out, for example, which part of the member would be under the maximum stress, either shear or normal stress. But what we have was like, we didn't, at the time, we didn't care that, okay, if this is a maximum normal stress or if this is the maximum shear stress, is it gonna fail or is it okay under that? In this example, it's kind of the very first example that it asks you for the design. So when you want to design something, usually it's the other way. So you're given a material, so for example, you want to use aluminum, and these are how much the aluminum can handle. And then these are the forces. The forces usually is constant. For example, if you want to design the wing of the airplane as aluminum, and the forces are there, so it's not that you can play with the force. So the force, you know that. The material, you know. Then you will ask, okay, what's the size of the wing? That we make sure it's not going to fail in the middle of the air for any reason. This example is like that. So the force is given, the material, the material property is given, and they said, okay, what should be the size of the member that we want to use? And most of this course is about this part. Usually you want to know it's the basics of the design, and then eventually when later on you get to the more advanced design course, this is exactly the procedure you're going to use, but you're following the federal or the state codes to make sure that's not going to fail. So here it says that we have an object look like this. And there's a hole here. There's a hole here. And that object is going to be bolted like this into the pins that hold it into place. Okay, you understand? So it's the object, it has two heads, there's two holes, and at the hole is bolted to whatever it's holding. And then it will pull with 120,000 Newton. So it's going to be the 120 Newton. So it's pulling it. the plate that we want to use to build that, we know that we have a plate or the sheet of metal or whatever material. The thickness of that plate or the sheet of plate we have is 20 millimeter or something. It's 20 millimeter. So we know that the thickness, the T is always 20 millimeter. So we know our thickness, okay, so normal to the surface of the board. The thickness of that is always 20 millimeters, so we cannot play with that. And then it says that for the, and it's the steel. So the maximum allowable stress, the normal stress. So the maximum allowable normal stress is 175 megapascal. The maximum normal stress that can. The maximum allowable shear stress that it can handle is 100 megapascal. And the maximum bearing stress that it can handle is 350 megapascal. So, if this is what we have, it wants us to say, what's the diameter here? What's the diameter of this? What's the diameter of the hole? What's the height of that bar? So basically, what's the design of that shape?
I'm assuming we want to keep it as small as possible without failing.
That's true, because if we make it larger than we need it, then it's economically might not be good. So yes. Okay. So what would you do if you are given this?
Since it's under tension, we know that the failure points are going to be the joints, or where the holes are, I guess. And so we need to make sure that those are able to maintain that force.
So the holes is usually the weak point. But if I make this large enough, then maybe this becomes the weak point. So the hole is the weak point if the entire section has the constant height. But if, for example, here I make it very big and very small hole, then here might be. But I agree, just by looking at that, the weakest point is going to be the hole. So probably the first place we have to check is where we have the hole. Then what? So if I get the hole right, is it going to be okay?
We would then use that size and test the rest of things to see, because like we'd have to test the bearing on first and to set the hole size, and then using that we can set the rest of the sizes and see if they would work.
I agree. So assume I have the hole size. Then what about the rest of the sizes? Because you want to send it for manufacturing, so you have to have the entire sizes. You have to have all the dimensions.
So you need the one in the middle.
So yeah, also we need to check where in the middle, because if we get the whole size correct, but the middle is going to be too narrow, it may break in the middle. So there's two places that we want to check. But if the hole is right, and the hole size is right, and the middle is right, still that thickness can cause a problem. Right? So they're gonna also to look into that as well. So let's start with the hole. If I want to start, what's the hole size? What should I do? So check fine. So I want to find the hole size. So I'm gonna just draw it, the shape of the
Wouldn't it also depend on the thickness of the screw? Or are we just saying that the screw is the same thickness as the hole?
what do you mean inside the board?
The pin. So like, is it 3/8 diameter, or is that we're saying that the hole is the same diameter as the pin we're gonna be using?
Yeah.
Okay.
Eventually, when you want to do it in the engineering design. So right now we don't care about that, but when you want to do it, when you design it and you count for example, you count for 2.5 millimeter, you have to go and look at to see if do you have a 2.5 millimeter or 20.5 millimeter bolt. If you don't have it, you have to select the bolt that you actually can buy. So you will usually go up until you get to the first available bolt size.
Yeah. Okay.
But here, probably we are not going to check for that, but that's what you do when you do the design. So I'm going to draw the shape of that. This connection is going to be look like this, so it's going to be connection looks like this. So if I look at it from the top, so it's top. If I look at it from the top, the connection is like this, and the pin is here.
So the piece in the middle is the piece that we're dealing with.
Yeah.
Pieces on the outside, we don't have to worry about.
No, these two are the support, or these two are the one that put the force on that, and this is the middle one that actually we're dealing with. So if I draw the pin and break the pin, so the pin is gonna be look like. If it breaks it, it will break like this, correct? So if I have 120 here, I'm gonna have how much here? At the breaking point I have 60,000, correct? So now that I have that, so here, the shear stress, the maximum shear stress. So I know that the tau is F/A. But my shear stress here, I know already how much it is. So instead of having it like that, I would say, no, because I'm designing, I'm not calculating. I would say the tau that I can use should be equal to F/A. Correct? So the tau that I can have should be that. So how much the tau that I can have? 100 times 10 to the 6. Right? And then what's the force that I applied on the pin? 60,000. What's the area of the pin? I can use it, because I want to use it as a pi d2/4. Or if it gets you confused, I can write it the other way. It's easier to see what happened. Pi r squared. So find the d.
I got a
0.0275 meter. Or it's gonna be 27.5 millimeter, right? So, if it was the engineering design, I have to go and find the first bolt that I have larger than 27 millimeter. So if the first one is 28, I'm gonna use 20. If the first one is available in the market is 30, I'm gonna use 30, correct? So that's the minimum size, remember that. That's the minimum size. My hole should be, so look at it this way. If I make the hole bigger, is it gonna make it worse or better?
We'll have to adjust everything, but it should, if you make the hole bigger, then normally it would be stronger. Because you're using a bigger pin, technically.
Yeah, so the pin is stronger, the piece is gonna be
Weaker.
weaker.
But yeah, that's why we'd have to adjust everything.
So this is the minimum diameter for the pin. So this is the minimum diameter that we make sure the pin doesn't fail. Okay? So that hole, so it's gonna be, we are gonna choose the, or find the pin size, because probably it's bigger rather than the hole size. So we are gonna just choose, the book choose 28, so we're gonna say, okay, we choose D equal to 28 millimeter. So now that I know that that's the size of the hole, that's the size of the pin. So my pin should be at least 28 millimeters. So I need at least 28 millimeter hole there. So now that I have a 28 millimeter hole there, I have to make sure that part is not gonna fail. Okay, so I'm gonna find the size of either of these two to make sure it's not gonna fail there. So next part is find head size. So at the head, if I cut it here, if I go and cut it, which one is it? If I cut it, you can see it better. Let me cut it here. So if I cut that there, okay, if I cut it at this section, assume it's section 1. If I cut it there, what I'm gonna have is gonna be something like this. So the sizes that I have is, I know if I have these, assume I call this A, I call this A, and this is 28. The area that the force is going to be subjected to the force is going to be this area and this area, because it's tension. And how much is going to be at each of them? So 60 and 60. How much is here? 120. You agree? So now how do I find the size of A?
We set the normal force to 175 megapascals and
Yep.
solve.
Yeah, so we know that that's the normal force. We want to make sure that our normal stress is not gonna be more than 175. So I can go ahead and say, again, the allowable shear stress that I can have is force divided by area. So 175 times 10 to the 6 is equal to the force that I have. I can use the both area, I can just use one of them because it's symmetric. If it was not symmetric, I have to use the entire area. It's symmetric, I can use one of them. So I can say the force is 60 times 10 to the 3, and the area, how much the area? So the thickness is
20 millimeters.
20 millimeters, so it's always 20 millimeters. So if I go and let me write it up here. If I say it's 60, so the thickness here, that thickness is 20 millimeters. So the area is basically T times A, correct?
Yeah.
No. The T is T is 1020, and it gives you the A. How much you get for the A?
17 millimeters.
what's the rest?
0.142.
Okay. So that's ours. Millimeter. So if I go ahead and say this entire thing is B is here. So if I go and say this is B, this entire things. So the B is A plus 28 plus A. So B is 17.14 plus 28 plus 17.14, which would be, how much is that?
62.28.
62.8 millimeter, and how much?
28.
Oh, 28, 62.28.
Yeah, 0.28.
And the book says 62 point. Select it. So just write it here. 62.28. So we choose B as 62.3 millimeter. Again, when you want to choose it, you have to go and look at it, the instrument you want, because, for example, I said 0.3 millimeter is very fine precision. So you have to, the CNC machine you have, or whatever you're using, if that's precision you want, you can get it. If it's not, maybe you can go a little bit upper, for example, 63 millimeter. So what's left? The thickness of the middle part. So it's okay, what about the middle? So I have to go and say, okay, I want to check the thickness of the middle. Bar height. So if I go ahead and say, okay, you know, the bar that I have is look like this. And here the T is 20 millimeter. And this is the height. And the force applied on that, we know how much force applied on that. The height there. 120. And this is the H. And then we have the same things again. The allowable sigma we have is the force divided by area, so 175 equal the force, that is 120 divided by T times H. The T we know that's 0.020. So H would be, what you got? So look, we choose 35 millimeter. That's why I said probably here, if I would probably it's better to go for 63 rather than 0.3 millimeter. So are we done?
No.
What's that?
We have to check that this can all work together, that by us changing the size of one thing, we didn't weaken something else.
So we'll find all the dimension we need. So we have the bearing, still have the bearing. So for the bearing, the part is that if we want to find the pin size, for the pin size there are two things, is the shear and the bearing. So usually we can't design it for both. So we can design it for one and check for the other one. So we either design it for the shear and check if the bearing satisfied. If not, then we design it for the bearing and make sure that the shear is satisfied. So we have to go there and see, is the bearing is satisfied? So if I go there and say, hey, let me right here. Check bearing stress. So I have this size, though I have to want just to check for the bearing. So the sigma bearing is F divided by the T. The area of this cross section of the hole. The cross section area of the hole, which is going to be the T times D. Correct? If it's a D, it's a T, so it's going to be T times D. So it's going to be 120 divided by T, which is 0.20. And how much was the D? So how much is that? So it's a 214 megapascal, which is smaller than 350, correct? So we are good there. If it was not, if that fails, then we should have to find the pin size based on this one. So I said, if bearing fails, then we find pin size from bearing. But it didn't. Question question? So that is the very simple procedure to design a member. So we have to go and find the stress in every possible point that it might fail, and then design all the sizes and thickness in a way that we make sure we always stays below the breaking point. So that's the normal and shear stress. The first part. Do you have any question about the entire part before we go to the next section? So all I have up to this point was, if I cut and everything is normal to the surface, but if I cut it instead of normal to the surface, I cut it with some slope, level. Up to this point, I said, I assumed when I'm doing all the design and calculations that the cutting surface is normal to the member. What if it's like that?
You have to change the force, it's pointing out of the face.
So we have to go ahead and, as I said, we have to go ahead and find a component of the force on the new surface area. So once it was the stress on the oblique surfaces. So what we had up to this point was like, if you have a member, and that member is under normal forces, either, and then I go ahead and cut it somewhere in between, in the middle of that. What I'm gonna get is like this. I have the force here, and I have the internal force normal to that surface, equal to that at that point. And then I can go and say, hey, you know, I cut it there. And then I can say, okay, how that force is distributed over there, you know what, I want the distribution of that force rather than its magnitude. So it's going to be F here, and then I have shear, the normal stress here, and that's going to be sigma, which is going to be equal F divided by here. So that's what if I have this form of that. But if I go ahead and say, now, instead of cutting it like that, I go ahead and say, the same member, same forces. And this time, I want to cut it like this. This angle stay. So if I redraw it the same as here, I will have this cut like that, like this, and I have the F here, and then I have the F here. Agree?
Would it no longer be distributed, or are we just not there yet?
No, they're just up to here. So the internal force is the F. Now that we have it, we have to go ahead and say, okay, I want to know how much forces would be applied on either of the surface. I will go ahead and say one step further. Okay. If this is the case, this is the F. This is the F. How much forces, or what type of forces do I have on that surface?
Tension? So what you're asking?
The surface, here, I have only normal. What do I have? There are going to be two components, so if I want to break that into its components, it's going to be two components. So what are the components? You agree? I can break it into two components. So this one, for this surface, what type of force is that? No, it's a normal. What about this one? So what type of force do I have here? A simple tension, correct? So look at here, if I have a simple tension and I cut it, I only have the normal forces. But if I cut it with some angle, then I'm going to end up having both normal and shear. Although the members they're the normal force. So even under the normal force, I might end up with the shear. That's very important. That in later on when we want to design, even under the normal force, on angled surface, I will have the shear. So here, this one, which is the normal force, the normal is gonna be, how much the normal? It's gonna be F cosine theta. And this one is gonna be shear, which is gonna be F sine theta. Now if I go ahead and redraw that, okay. I'm gonna have which is gonna be there. So these are the sigma, so these are the normal. And I'm gonna have so this is gonna be off. How much is this area? We call it the A of the theta. This area would be the normal divided by cosine theta. The A is the normal cross section. So if I know that, then I can go ahead and say, you know what? The sigma is the F divided by area, so it's gonna be N divided by area of the theta, so normal force divided by that A theta, which is gonna be normal force is gonna be F cosine theta, and the area is gonna be A divided by cosine theta. Agree? So the shear is also is gonna be again F divided by A, which is gonna be the V divided by A theta, which is gonna be F sine theta divided again by A divided by cosine theta.
And the first one, can't you write as F cosine squared over A?
Oh yes, I'm gonna simplify it.
Oh, okay. I'm just making sure that wasn't like a reason or something.
So this one, put it a 0, so we know that we know when the theta is 0, so when it comes there, put the A 0 there. So I can go ahead and again rewrite them as it says, so I can go ahead and rewrite them. The sigma is F divided by A0 cosine theta squared, and tau is F divided by A0 sine theta cosine theta. So these are going to be my normal and shear stress on the plane that has the, on the surface that has an angle of theta. So here, the points that even under axial force, we have here on oblique surface. When it's completely axial force, right? And up to here, what we have just said, okay, it's the axial force is going to be under the normal stress, but it's not like that. We can have the shear on the oblique. So why we actually interested in the oblique plane? Why not only use the normal surface?
We don't know what it's being, well, it might be set up in a way that it could break at an angle instead of breaking at a normal plane.
That's exactly right. If you have the complete material that in all directions have the same properties, still it might break with the angle. There's no guarantee that it's going to break exactly right in the normal. And if you get worse, if you have the material that its properties is different in different direction, then when you pull it, it doesn't say that exactly it's going to break in that direction. It can break. It might be weaker in other direction and break in those directions. So, let me take a picture of that. I go ahead and cut that plane, so again, I'm gonna redraw that. If I go ahead and say, hey, I have the same things here. I have the forces of F lying at both ends. And then this time I'm gonna cut it, but I'm gonna cut it with it with I'm gonna cut it at 45 degrees, exactly 45 degrees. So I cut it at 45 degrees. That's gonna be F. F. Here I'm going to have its component. N and V. And this is 45. And N is going to be F cosine 45. And V is going to be F sine 45. And then I'm going to again as it. Sigma. It's going to be tau. For theta 45 degrees, I have the sigma is gonna become, if you write it, it become F divided by A naught for theta equal 45 degrees. So it's sigma for 45, the tau for 45. The tau would be also F divided by 2. Look at here, what's about this N and V? So at 45 degrees, N becomes equal to V. Agree? Therefore, the magnitude of sigma at 40 magnitude of sigma at 45 degrees is equal to magnitude of tau at 45 degrees. So look at these two equations. When sigma become maximum?
When did it?
When it becomes maximum? If I start to cut the plane, start from normal and keep cutting at the angle. At what angle the sigma is maximum?
When cosine is 90. Or when the angle is 90.
So, no, look at the theta. 90 is horizontal.
Oh yeah, when it's 0. Wait.
It's 45.
When that part is constant. So when the cosine theta is maximum,
When cosine is 0.
and cosine is 0. Cosine 0 is 1. So we get the sigma max. So at theta is 0, sigma becomes sigma max, and the sigma max is equal to just F over area. So the normal, if I cut it normal to the surface, the sigma is maximum. So if it wants to break under the normal shear stress, it will break under the theta 0. What about the tau max?
45.
So the tau become at theta equal 45 degrees. The tau will become tau maximum. And how much the tau max? Just the same things here. So the tau max would be F divided by 2 A naught. So if our member wants to break under the normal shear, it breaks at the 0 degree. If it wants to break under the shear, it will break at 45 degrees. Got it? So member fails under normal stress at theta equals 0, and it fails under shear stress at theta equal 45. Remember that is for, what's that for? For axial force. If you have on the axial force, if we have other type of force, if you have the bending and we have the shear and we have the torsion, that's not correct. If we have the pure axial force, okay, is the pure axial force, it only breaks for under the normal when the theta is 0, under the shear when the theta is 45 degrees. later on we will use these concepts in the design. So in the previous one, when we did the shear, we just assume it's normal. But later on we will have to go and look at the angled one. But the conceptual, any question about the concepts? Part is that. So up to here, what we have was only the 2D. Now we want to actually, because the object is 3D, so we want to start looking at the object in 3D. So, okay, if the object is in 3D, then how the stress would be there. So we're going to look at the stress in 3D. What are 3D cases as I have it? Because the axis is a little bit rotated. It's the X, Y, Z. Rather than the normal one that we always have. And then we will have an 3D object. So that's a 3D object, I cut it somewhere in between. Somewhere in the middle I cut it, okay? And then I go and look at a very small area in that. So go there, okay, I will have an element there. There's the element there. Small element I want to look at. So what type of stress I can have on that point? So one can be completely normal to that, agree? So I can have the normal shear stress. How many shear I can have?
How many different types of shear can we have? But we can also have one heading towards the Z direction and one towards the Y direction. And
So, yeah. Any other? So I can cut it from top to bottom, or from left to right. Can I cut it any other way?
Any way that's parallel.
Say that again?
You can, but it's just maybe flip the arrows. Like if you cut down, okay, it's the same thing as cutting up.
Yeah.
As long as it's parallel to that front surface, it's gonna be a shear force.
Yeah. So, I only can have two shear forces. One going either up and down, or going to the board, or coming out of the board. Correct? So I can have two shears, so one I can have in the direction of the Y, and one I can have in the direction of the Z. And this is called TXY. This one is called tau XZ. So points. If the sigma 3D is positive, it means that what does it mean? It means the surface is under tension, like the 2D. So the positive sigma is in tension, the negative is compression. The next is that tau xy, it means that tau on surface perpendicular to x and in the y direction, or in direction of y. Direction of y. So what does it mean? Tau normal to x in y direction. This one is tau normal to x in z direction. You got it? So the first letter is the norm, it shows the normal axis, the second letter shows the direction. Here, x is normal to the x in the direction of the z. Here, normal to the x in the direction of the y. So that's how we read the tau. And so that's the normal to the x. Any question? Now if I go ahead and say, okay, I'm gonna Now if I grab that element and bring it out, I want to, that element I have, the same thing as the x, y, z. Now I want to draw that element in the 3D format. So I have element in 3D. And now I want to show what's happening on that. So on each surface I have a normal stress. On each surface I will get a normal stress. So if I have it here, that's the normal stress, and it is sigma in the direction of x. So it's the sigma x, I will get the normal in the direction of the z, and get the normal in the direction of y. And I have these three on the other three surfaces. Exactly the same thing, the other three surfaces. What about the tau? How many tau I have on each surface? Similar like here. On each surface I will have two taus. So one in each direction. So for example on the here I will have tau yx and tau xz. Tau zx, tau zy, and then on the top surface tau tau yz, and I have the exact same on the opposite surface. So the same thing will be on the opposite surface.
How do we decide the order of the letters again?
The first one is shows what surface is a normal to. So here, the top surface, is it which axis is it normal to?
It's
It's normal to the-
y.
So the first letter is y.
Yep.
Because the surface is normal to the y. The second letter shows the direction. So it's gonna be, this one is in direction of the x, and this one is in direction of the z.
Then I think you have I think that tau yx is, because it's on the one
So
surface. is
that's
x.
x, y. You're right. X, y. Yeah, thank you. So these are tau y, tau x, tau x. And these are tau z, tau z. Okay. Are the rest correct?
Yeah.
Now if I go ahead and I try to say, okay, I want to make it 2D, I want to draw it in a 2D to see what happens, because usually we use it in the 2D cases. So on the XY, I want to see what happens if I go ahead. Only I want to draw the XY. So if I draw the XY, only the XY. And draw my element there. Okay. This is my element. So I'm gonna have the normals. That's gonna be sigma x, and then I will have the shear, and the shear is going to be normal sigma x, sigma y, sigma y. That's a normal, and then I have the shear, which is going to be all yx. It's going to be tall xy. And then these two, which is going to be tall y. Tall xy. So it's going to look like this in 2D.
So when dealing with 2D, we don't need to worry about arrows coming in or out of the board.
No. So look at that. Under what condition that is in equilibrium? That element.
When all the tiles are equal to each other, or when all the I forget what the other symbol is, are equals, or they cancel, or they have to be able to cancel each other out. Like, things need to add up to 0. What? If it's not tau, what's the other symbol? Alpha? No. Sigma.
quickly, this is the element I have. And then sigma x, sigma y, sigma y. So if I want to make sure it's in equilibrium, there are two things I might make sure it's not moving in the x direction, it should not move in the y direction, and it should not spin. So under what condition it does not spin? In the x and y direction, if I want to say, okay, these two should be equal, these two, so sigma xy and sigma xy should be equal, sigma y xy x should be equal, these two should be equal, these two should be equal, but does it guarantee that it does not rotate?
Well, no, because the way your arrows are set up, if the xy taus were equal, it would rotate anyway. The xy tau and the yx tau would have to be equal to cancel each other out.
So how it does not rotate?
You can't like spin this, I don't think.
The only way that it does not rotate is that these two is equal.
Yeah.
That's the only way it does not. Under any other circumstances, it will rotate. So the only way in the 3D it does not spin, the same way it's the only way that it doesn't spin in the 2D, we can extend it to the 3D. So based on that, the tau xy should be equal to tau yx, and the tau xz should be equal to tau zx, and the tau yz should be equal to tau zy. That's the only way that it does not rotate. In any other way, it will spin. And then look at the way I draw them. Even if this is correct, so if I have them like this, what will happen?
It will rotate no matter what. Unless one of the forces is somehow negative.
No, under that condition,
It's gonna spin.
it's gonna spin no matter what. What if I rotate it the other way? So it's gonna, this one is gonna spin like this. This one is gonna spin like that. So that can't be, that's not right. That's not right. So the only way that it's in equilibrium is that if I have it like that. The only way it's gonna work. Either I should have my shear coming like this, coming like this. That's the only two way. If it's gonna be one of these two, it's not good. So this is okay. This is okay. Agree? So to be in equilibrium, all four shear stresses must have equal magnitude and be directed either toward or away from each, not from each other, from each other at edge of the element. So, in other words, each edge I pick each edge. Each edge I pick, the shear all either going away from that edge or going toward that edge. Got it? So here is not right because one of them goes toward the edge, one of them move away from the edge. The same here, one of them goes toward the edge, one of them move away. But here, both of them goes, here, both of them move away. So at each edge you choose, either both shear should go toward each other or should move away from each other.
Do the shear forces at the top and bottom have to point in different directions from each other?
Yes,
Okay.
because it should, otherwise the sigma fx would not be 0. If both of them are in the same direction, the element would move in that direction. So they should be away from each other to make sure sigma fx and sigma fy